So once again, welcome to a new problem. We have cantilever running across towards the right, and it has two supports. There's one support that's on the right edge, and then there's another support that's close to the center, but not exactly at the center. I think I want to place it that way. The distance between these two supports happens to be 20 meters. So from right there up until there, you have 20 meters. So there are two forces. The right support has a reaction, A, because we're calling it A, and then that's the left support, sorry. And then the right support has a second reaction. We're calling it RB. This is B. The distance from the middle support or the right support up until the edge right there, that's 30 meters. That's the distance. The weight of the cantilever acts through the middle. The weight of the cantilever acts through the middle. Well, the mass itself, M, is 2,900 kilograms. That's the mass, and then we can always get the weight of this, so mg will be 2,900. Oh, you know what? I want to have it in kilograms. So 2,900 kilograms times 9.81 meters per second squared. That's going to be the weight, like mg of the whole thing. I don't want to think about the weight yet, but I just know that it's mg at the moment. The distance from the center up until the right edge is 25 meters. And then from this center up until all the way up until this side is also 25 meters, and that's from the center itself. Our goal, that's what's given in the problem. Our goal is to find the cross-sectional area. So, for the left one, for A, the cross-sectional area will be A here. That's the cross-sectional area of A. And then also you want to think about the cross-sectional area of B, which is this one. So if you cut across B, what's going to be the cross-sectional area? The system is in equilibrium. The system is in equilibrium. So that simply means that the sum of forces in the y direction is 0. So RA plus RB, because they're pointing upwards, so they're both positive. And then minus mg is 0. This is mg is pointing downwards, so it's negative. And so RA plus RB equals to mg. So the reaction at point A is RA, and the reaction at point B is RB. The sum of torques around A is 0. And so if you think about B itself, B is going counterclockwise relative to the point A, and then the weight is going clockwise relative to the point A, so the weight is going to have a negative torque, and the reaction at B will have a positive torque. But then the distance from the reaction at B up until the left edge A is 20 meters, so we have RB times 20 meters, RB times 20 meters. It's positive because it has a positive torque going counterclockwise. And then minus mg times 25 meters. uh, that's equivalent to 0. Now this is going to help us solve for RB. So RB equals to mg times 25 meters. Mg is the weight. Then we have to divide both sides by 20 meters, and that gives us RB in terms of the weight, so 1.25 times the weight. That's the fraction of the weight that RB is kind of like supporting. Then we're going to go to the next page, and since we know that the two reactions have to be equivalent to the weight, otherwise the system is going to collapse, we can solve for the left reaction, which is mg minus rb, using algebra. But then since from this previous page, you see rb is 1.25 of the weight, so we can always do those replacements and have this as 1.25 times the weight. And so Ra is negative 0.25 of the weight. The negative just means that it's in the opposite direction as the weight, so don't think about that too much. Rb or Ra now is 0.25 of the weight, and the second reaction is 1.25 of the weight. Those are the two reactions. Remember, our goal from the beginning was to get these two cross-sectional areas. So we're using equilibrium as a way of helping us solve for the two reactions. But we don't stop there, because we have to think about the stress at A. The reason why we think about the stress at A is because it's going to give us a relationship that has the area. And that's what we're looking for. We're looking for the cross-sectional area. So if we can figure out a formula, stress formula, that has an area, it's going to help us solve the problems. So the reaction at A is 0.25 of the weight, and then that's going to be divided by the area at A. There's another concept that will be helpful in solving this problem, and this is what we call the safety factor. And the safety factor is denoted by N. And in this case, for part A, the safety factor N is the same as 40 times 10 to the 6 Newton per meter squared in this case, and it's the relationship between the ultimate stress. It's the relationship between the ultimate stress and the stress at A, which we already have the formula for that in the previous page. And so if we plug in all the information we have, we've already got the stress at A, which was this relationship right here, 0.25 of the weight times the area. The cross-sectional area of A. And we can move up the cross-sectional area with the ultimate strength, ultimate stress, not strength. That's equivalent to the safety factor. So our goal is to solve for A. Our goal is to solve for the area at A. So the area at A will become, we have to multiply both sides by, just take note of this. We have to multiply both sides by the reciprocal, 0.25 mg, and I'm just highlighting that so you see how critical that is, 0.25 mg, and that helps us cancel out these and cancel out that. So we have the area at A being equivalent to the safety factor times the reaction at A, which is 0.25 mg, and we're dividing that by the ultimate stress, we're dividing that by the ultimate stress. And so the area at A becomes equivalent to N, which is the ultimate stress. The ultimate, not the ultimate stress, but the safety factor. So I think we need to make some changes here just to make sure we're on the right track. The ultimate stress, sigma, was equivalent to, just a correction right there, was equivalent to 40 times 10 to the 6, and then the safety factor was equal to 9. So just make sure that those two numbers are correct. So this is 9 times 0.25, and then the weight, so 2,900 kilograms times 9.81 meters per second squared. And then we divide that by the ultimate stress. We already rectified that. So 40 times 10 to the 6 Newton per meter squared. And so the cross-sectional area at A, we got it now, is the same as 1.6 times 10 to the negative 3 meters squared. That's the cross-sectional area at A. Now, in the next page, we want to get the cross-sectional area at B. We've already dealt with the one at A, so now we're dealing with this one. It's the same process, so all we have to remember is that the stress at the reaction B, this is the stress at B, is the reaction at B divided by the area at B. The reaction at B is 1.25 of the weight over the area at B. Safety factor is still 9, but it's the relationship of the ultimate stress and the stress at B, in this case the ultimate stress. For the second portion of the problem is the same as the ultimate stress for the second portion of the problem is the same as 35 times 10 to the 6 Newton per meter squared. And so our goal is to get that area. I'm going to clarify it a little bit. So the area at B is the reaction at B over the stress at B. But then if you look at this problem right here, from this part, we could say that the stress at B is the ultimate stress of the safety factor. So this is the reaction at B of the ultimate stress with the safety factor. So the area at B comes equivalent to the safety factor, reaction at B over the ultimate stress. So that's the formula we're going to be using, and we can jump onto the next page. So now we know what the area at B is. It's the safety factor, reaction at B, over the ultimate stress at B. So not the stress at B, but the ultimate stress. So this one is the ultimate stress. So then the cross-sectional area at B, safety factor, reaction at B, remember, if you go back, was 1.25 of the weight, 1.25 times the weight over the ultimate stress in the second portion, which is 35 times 10 to the 6 Newton per meter squared. So this is 9, 1.25, 2,900 kilograms Then don't forget the acceleration due to gravity, 9.81 meters per second squared. Then divide by 35 times 10 to the 6 Newton per meter squared. So then the area at B is 9.1 times 10 to the negative 3 meters squared. So, once again, we have two portions here. We have the reaction at we're looking for the cross-section at A and the cross-section at B. The first thing, we have to use equilibrium to find out what these reactions are. So reaction at B is 1.25 and the weight. And then using that, we can always get the reaction at A, again using equilibrium. Don't forget about the torque. So the torque was helpful to get the reaction at B. And then after that, we have to use the stress at A to determine the relationship between the reaction at A and the area at A. That way we expose a formula for the area at A. And that formula is the same as the ultimate, the safety factor, the reaction at A, and the ultimate stress. We end up getting 1.6 times 10 to the negative 3 meters squared. Then we repeat the process. We're going to get the cross-sectional area at B using the same process. So it's a component of the safety factor, reaction at B, and the ultimate stress. We use different ultimate stresses. This one is 35 times 10 to the 6, and the previous one for A is 40 times 10 to the 6. And we solve for the cross-sectional area at B. So hope you enjoyed the problem. Feel free to send any questions or comments and have a wonderful day. Okay, thanks, bye.